Welcome to this new lecture of Robotics 2. Today we will consider a new alternative method for achieving regulation in the presence of gravity. We will use a simple version of what we can call an iterative learning scheme that acquires information while doing the task in order to compensate exactly the gravity at destination. So our objective will be to handle the presence of gravity, but differently from what we have seen in previous lecture. We don't use information about the model, in particular about the gravity term, nor for cancelling gravity in every configuration, nor for compensating gravity at the destination. We don't make use of high positional gains, which would reduce, although not eliminate completely, the position error at steady state. And differently from the use of PID or saturated PID, we would like to find a control scheme that does not require special condition on the control gain to be chosen, which would guarantee convergence. Now, the scheme is based on iteration that are not repeated trial of the same motion task, but require some intermediate stage while moving toward the destination. The control law is very simple, is a PD control on the joint position error, to which we add a constant feedforward term. If we had the knowledge of the gravity vector in the dynamic model, this constant feedforward term would be the gravity at the destination, so G of QD. But we assume that we don't have this knowledge. So we will iteratively update this feedforward term while we move from a steady state condition to another under the action of this control law. The goal is to verify if we can find sufficient condition that guarantees a global property to this iterative scheme, so convergence to the desired state with zero final error both in position and velocity. Velocity for regulation task should be zero at destination, so this is not our main problem. So we will use a couple of preliminary results. In particular, given the robot dynamic model in the usual Euler-Lagrange form, we assume the existence and the knowledge only of a bound on the gradient of the gravity vector term. We have seen that the G over dq is indeed a symmetric matrix, not necessarily positive definite. So the norm will be of this matrix will be the maximum eigenvalue of the product of the matrix by its transpose, and then extracting the square root. So we assume that this quantity, this norm, is upper bounded by an alpha. And alpha, of course, can be very conservative. Now, if we try to regulate a desired position for this robot, for a generic robot, using a joint error and a PD law, so without considering the presence of gravity, nor cancelling, nor compensating gravity at all, so we would apply a PD control of the form shown in the slide, with typically positive definite and symmetric KP and KD matrices. Typically we choose those as diagonal. Now we know that this control law cannot regulate the desired configuration because it does not provide at steady state, if at the desired steady state, namely when the error in position is zero and the velocity is zero, the torque which balances the gravity at the destination. So for a generic task, this will not work. So what happens is that we will find at steady state an equilibrium which has a non-zero error left. Let's call this equilibrium configuration Q bar, and since we are at steady state and this is an equilibrium, necessarily, as we have seen for mechanical system, Q dot should be 0. So we implicitly know that at this steady state, the residual error Qd minus Q bar multiplied by the gain balances the gravity in that configuration, which is not the one which is desired. So we have an error E bar, which is the difference from Qd between Qd and Q bar, and this is different from 0. Now remember that this steady state may be different in general from depending on where we started and what type of proportional gain we are using. But anyway, whatever this steady state will be, there will be an error. So the idea is to slightly modify the PD control by two changes. First, we add a constant compensation term, and since we are assuming that there are iterative stages in our control process, we will start with in the first iteration, so I equal 1, with a U0, and then after a while we will update this to a U1, U2, and so on. And this is the first modification. The second modification is that we add a factor gamma to the proportional matrix gain. This gamma is a simple scalar that we take as positive. In the rest of this presentation, without a lot of generality, we will consider that the Kp and Kd matrices are chosen as diagonal and positive definite. We label Q0 as the initial robot configuration where we start from with 0 velocity, and we have to initialize our feed-forward term, and the easiest initialization is no knowledge about any useful information, so we set U0 equal to 0. Now if we apply this control, so in the first iteration this will be exactly the PD control with some positive gain gamma added to the proportional matrix, we will find a steady state which in general is not the one desired, the QD desired. So let's call the steady state iteration, steady state at the ith iteration with Qi for the configuration and indeed Q dot 0 for the velocity. The balance will be between what we are applying in this steady state, so our control law with Q dot equal to 0 when we reach a configuration Qi, a generic, so it will be gamma Kp times Qd minus Qi plus the current feed-forward that we are using in that iteration. This will balance the gravity at this configuration that we have reached. Now, when we reach this steady state, and which is not the right one, we update the feed-forward term only. So for the next iteration, we will restart because we change our ui minus 1 and we replace it with ui, which has this formula, which is nothing else than the control effort that we are applying at steady state at the end of the ith iteration. This will become the feed-forward term only in the next iteration. Now, indeed, because of the previous equation, the update is made by a torque term which is equivalent to the gravity at the previous reached steady state. We don't know a priori what is this gravity, but we know its numerical value because it's exactly the control effort that we are applying in the known reached configuration Qi. So from there we can do the update law. So we will, in the implementation, we will use the expression on the left-hand side, But we know that for analysis this will be equivalent to the gravity in the configuration that we have just reached. Now we have a theorem that proves convergence of the sequence of steady state configuration that we will reach, starting from a generic value Q0 and then proceeding over the iteration. The theorem says that if the minimum eigenvalue of the diagonal positive definite matrix Kp is larger than alpha, remember that Kp is diagonal, so this is also the minimum eigenvalue is also the minimum element on the diagonal of Kp. And moreover, if we choose the factor gamma larger or equal than 2, a simple number, then we can prove that the sequence converge to Qd. Indeed, since we are converging to a new equilibrium, then even Q dot 0 will be 0. And this holds starting from any initial value of Q0, and in principle we could also start with a non-zero initial velocity. And this occurs globally. Now let's comment these two conditions. The first one is already known, is in fact the condition that guarantees, so the sufficient condition that guarantees that we obtain global asymptotic stability if we are using a PD plus exact gravity compensation at destination. So if our feed-forward term is exactly the one needed at the destination, so G of Qd. So we have to know the gravity term at the destination, and since this Qd may be any in the robot configuration space, we should in fact know the whole gravity vector functional form. The second additional condition, so condition B, guarantees that the iterative scheme under the hypothesis of A will converge, and in fact we will have that the converging sequence for the feed-forward term will eventually be the unknown, a priori unknown gravity term in the desired configuration. The proof uses a concept of contraction mapping, and this is interesting per se. It is quite simple. So let's define E sub I as the error reached at the end of the ith iteration. So Qd minus Qi. And now we update our feed-forward term, and we know that at the end of each iteration this update will be equal to the gravity acting at that final configuration Qi. So if we make the difference between two updates, Ui minus 1, this will be the difference between the gravity at the configuration Qi and at the previous configuration at the end of the previous iteration Qi minus 1. And by the bound that we know on the gradient of the gravity vector, this will be less or equal than alpha, the norm of the difference between these two configurations. And now we make a conservative bound. So we add and subtract from the last term the desired Qd. So we build the error Qi minus Qd and Qd minus Qi minus 1. So the error at the end of iteration I and the error at the end of the previous iteration. And we replace this with the sum of the two norms instead of having the norm of the sum. So this is quite a conservative step, which will make this condition actually sufficient, in fact. On the other hand, if we look at the update is Ui equal gamma kpi ei plus Ui minus 1. So if we reorganize term and we take the norm, and since gamma is a positive scalar, can be taken out of the norm, we have that the difference between Ui and Ui minus 1. So remember, these are the feed-forward term in two successive iterations. will be equal to gamma norm of Kp EI. Now if we put together these two equations, we can substitute ui minus 1 in norm in the first equation and have that, look at the right hand side of this chain of inequalities, that gamma times the norm of Kp times the error at iteration I is less or equal than alpha, the sum of the norm of the error at the end of two successive iterations. Now if we go backward in these inequalities, indeed the norm of the matrix Kp times the vector Ai can be lower bounded by the minimum eigenvalue of the matrix Kp times the norm of the vector Ai. And by the first assumption, assumption A of the theorem, the minimum eigenvalue of Kp is strictly larger than alpha. Now, if you look at the first and last of this chain of inequality, taking into account a strict inequality in the first place, you can divide by alpha, so alpha becomes irrelevant in this in the sequence, and then divide by gamma, so you have on the left hand side the norm of EI, so the error at the end of iteration I, is strictly less than 1 over gamma, the sum of the norm at that iteration plus the norm at the end of the previous iteration. Now if you reorganize this inequality, so you bring the norm of the error at the end of an ith iteration to the left, you will have 1 minus 1 over gamma, strictly less than 1 over gamma, the error at the previous iteration. And then you divide by this, you simplify, and you end up with this very simple equation that says that the norm at the end of iteration I, the norm of the error, will be strictly less than 1 over gamma minus 1, the norm of the error at the previous iteration. So the second assumption, which says that gamma should be larger or equal than 2, it means that 1 over gamma minus 1 is less or equal than 1, and since the error at the end of the ith iteration in norm will be strictly less than this, so it will be strictly less than 1 times the previous error, we will have that from one iteration to the other, the error will contract towards 0. So this is in fact a contraction mapping, so eventually it will converge to norm of the error equals 0, which is exactly the thesis. So we have achieved asymptotic convergence, asymptotic as iteration pass by. We have not included any stability condition for this, and in fact we don't need to have stability or to prove stability for this to converge. So if you look at the overall behavior, the robot will move from one steady state to the next steady state, and at every new steady state it will update the feed-forward term. Now there are three gains involved in this very simple iterative scheme, the Kp, the Kd, and the gamma. Now the Kp and Kd will affect the transient during each of the iterations. So when moving from one steady state to the next one, the time needed, the overshooting, and the damping that we impose will depend on the choice of Kp and Kd. But eventually we will reach a new steady state. Now gamma instead, as you can see from the first formula in this page, will affect the convergence rate from one steady state to the other until you get to the final desired one. Now, if you combine the gamma factor and the gain Kp, knowing that the gain Kp, the diagonal gain Kp, should have the minimum value on the diagonal larger than alpha, and gamma should be larger or equal than 2, so you can redefine a new proportional gain matrix Kp hat, and the two conditions require only that we double the minimum value of Kp hat with respect to the case of knowledge of the gravity term. So, since everything is diagonal, this implies that the minimum element in the diagonal should be greater than 2 alpha. Again, as we have seen in many of the previous proofs, this is only a sufficient condition. So, if you choose Kp hat, I would say at this stage, larger than 2 alpha, for the minimum value of Kp hat larger than 2 alpha, then you're guaranteed that you will converge. If you fail to do so, the scheme may converge or not. So, in this sense, this is only a sufficient condition. Now, it's a nice interpretation of what we are doing is in terms of the addition of an integral term. In fact, every time we update our feedforward, we are using the story of the error so far up to the instant in which we state that we have reached a new steady state. So instead of continuously updating the integral term by using the error along the transient, we are using only the error reached at steady state, successive steady state, in order to update this term. So it's kind of a discrete version of the integral term, but discrete in the sense of events. So updating the integral part only at given instant of time, and not accumulating the error over the transient. And the nice thing is that in this case, in this simplified version of the integral term, we have guaranteed convergence and global asymptotic stability, in fact, without particular condition on the Kp and Kd gain, only a slightly larger value for the Kp hat gain. So let's see a numerical example of this situation. Suppose that we have a 3R robot with equal link length, 0.5 meters, uniformly distributed mass, so they're the center of mass at the half point of these links, moving in a vertical plane, so fully subject to gravity, and that the masses of the 3 links are decreasing, 30 kilograms for the first one, 20 for the second, and 10 kilograms for the last one. If we model with the potential energy and then the gravity term, so the gradient of the potential energy in symbolic form, and we plug in those numbers, then we can easily find that the value of alpha that bounds the gradient of the gravity term is around 400 for this case. So our theorem says that if you choose the Kp gain diagonal and the least element in the diagonal, in this case a 3 by 3 matrix, is at least 800, then you're guaranteed that you will converge, that the sequence of iterative learning of the gravity term will converge. In the simulation that we have made, we also included, for making it more realistic, some maximum bound for the applied torque, again decreasing from one joint to the other, so 800 Newton meters maximum for the first joint, 400 and 200 for the following one. And we have considered 3 case studies. We start in every case from the initial downward equilibrium position, so 0, 0, 0 is the 3 links are straight downwards. So this is, I would say, a stable or asymptotically stable equilibrium, unforced. So if we perturb a little bit this configuration, the robot will go back to this one. So we start at rest from 0, 0, 0. In the first case, we would like to move the first link by 90 degrees while keeping second and third straight. So from straight downward to straight horizontal. In the second case, we will make a higher motion, so we will move 45 degrees more, so a total of 135 degrees for joint 1, and joint 2 and joint 3 at the end should be again straight, so that the link, the robot is in the straight configuration. And the third case is the same goal, but with different gains. In fact, for the first two, we use for KP hat a diagonal matrix with 1,600 and 280 as gains, while the KD, which should only be diagonal and positive, in fact, the requirement of diagonality is not needed, but this is a simple choice, is chosen as 200, 120. There are no requirement other than having positive values here. Now you can see that the first gain on joint 1, 1,000, is larger than twice alpha, but the other two are smaller. So in fact, the smallest element on the diagonal of KP hat is 280. So in principle, we have no guarantee that we will be able to converge. In the third case, we will use a higher lowest gain, but still below the twice alpha value, which is 800. And the KD is chosen as before. We will see that the behavior will be different between case 2 and case 3. So with this in mind, here you can see on the top row the joint position error. Remember, you're starting from 0, 0, 0, and you like to reach the configuration pi over 2, 0, 0, so the horizontal straight arm. And the vertical blue lines represent the end of each iteration. So you start with a pure PD, and when you are reached a 3-second steady state situation, you update your feedforward, which becomes from 0, it becomes the value of torque that you are applying at that joint at the end of the first iteration, and then you restart moving. At 6 seconds around, you reach a new steady state, you update your feedforward, and then at the end of the third iteration, you are practically with 0 error, you're below some threshold, some numerical threshold that you can choose a priori. And this is done for all 3 joints at the same time. And you can tell from the second row of plots, which are the control torques being applied during the iteration, that you will start with some oscillatory behavior of torques until you're stabilized to a certain value. When you update the control torque, in fact, you update only the feedforward term, so you're changing the torque that you're applying. So the torque is no longer the one that guarantees to be in an equilibrium, although a false equilibrium, not the desired one. So you see that the torque has a jump, and this will make the robot restart. And this happens at the end of the first iteration, at the end of the second iteration, and at the end of the third iteration. There's no need to update the torque, the feedforward, because we already reached convergence. So convergence is in 3 updates in about 9 seconds of transient. In the second example, we have to overcome the, let's say, this straight arm configuration on the horizontal line is in fact the one where the gravity load is the maximum. So we have to overcome this maximum gravity load configuration in order to reach the 135 degrees of joint 1 with respect to the downward vertical, and again with the second and third link straight. You see that here the situation is similar, but in fact you may recognize that there are, I didn't put here the vertical lines, but you can recognize a situation where the motion of the joints stops. In fact, the error with respect to the desired configuration does not change. At this point, you have an update of the control torques. You can tell also when the update occurs by looking at the control torque profile, because when you see a discontinuity, this is exactly when we are updating the feed-forward term, so the control torque will have a step change. And you can see that there is one iteration, the second iteration around 6 seconds here, 3 seconds the first, 6 seconds the second. Every 3 seconds, more or less, we are updating things, and we have, in this case, convergence after 5 updates. So at the end of the 5th iteration, we converge to the desired configuration. So these two convergence cases are, in fact, despite the violation of the sufficient condition on the lowest gain. So you may think that in this other case, when we reduce the highest gain, but in fact we increase the lowest one, this case is the same task as the second case, but with proportional gains or equal to 500. So the lowest gain is larger than alpha, but still smaller than 2 alpha, which would be 800. So what happens? You can see that after some, let's say the first and second iteration, the behavior becomes repetitive. In fact, the joint position error does not converge to 0. So you see that after about 6 seconds, I would say, the joint position error has stabilized. So we do the update. We have a new equilibrium state being reached at the end of the second iteration, but from there on, the system repeats a motion from one equilibria to another equilibria and back. So there is a limit cycle in a sense, but no convergence to the desired equilibrium, which is with the configuration 3 pi over 4, 0, 0. And similarly, you can see that the control torques becomes periodic, but this is not, so the system is not diverging, but is never converging. It stays to some kind of local minima, from one local minima to the other local minima, a bit above the desired value of Q1, a bit below, and with the other two joints also not placed correctly. In fact, you never find a 0 in the upper plots for any of the 3 joints. So you see that the system cannot converge if you violate the sufficient condition. It may converge if you violate, and it certainly will converge if you don't violate the sufficient condition. So, final comments on this very simple law. It's a first example of learning, in the sense that without knowledge of the model terms, in particular of the gravity terms, but also of any other terms of the dynamic model, only a bound, an upper bound, is known on the gradient of the gravity terms. So without any a priori knowledge, by applying PD control plus this special kind of feed-forward, we learn something at every iteration. We learn from the error, in a sense, from one iteration to the other. And this error allows us to learn the correct gravity compensation at the destination. Of course, if we have a new task, a new desired QD, then what we have learned so far is more or less of little use. So we could start with U0 being the learned term for the current configuration, which is the end of the previous task, but from there on we have to learn again online what is needed. So this is a comment that I already made on the sufficiency condition on the proportional gain. And in fact, when you see that violating the sufficient condition you don't get the expected results, this gives you also a measure of distance between the sufficient condition and the necessary ones. Of course, if you by chance find that every time you violate the sufficient condition you fail, then it's very likely that your sufficient conditions are also necessary. But this is not the case. Now there's another comment which is kind of explaining why we get convergence despite we fail to satisfy the sufficient condition in terms of the gains. And the fact that this lower bounds that we have to satisfy takes into account the robot as a whole. There's no detailed analysis of the fact that in order to overcome this local minima of gravity action which prevents the scheme to converge, we don't consider the difference between links in the serial chain. Now, with reference exactly to the considered simulation case study, it is rather obvious that the last joint will have to sustain under gravity only the last link. The before last joint has to sustain under gravity the second link and also the third one. And so, going backward to the base, the first joint has to sustain the gravity load of the whole, of the entire robotic structure. So in this planar case, things are particularly obvious, but this is in general pretty much true for all serial manipulators also moving in 3D. So implicitly, one would say that the gains at the first joint in the sequence should be higher because they have to overcome the gravity effect, which is larger because it includes more links in the picture. And the smaller gains, the lower bound for the gains on the distal joints is allowed to be smaller. But indeed, one should refine the analysis in order to prove this, which is, for me at least, an intuitive result. And this explains also why in the first two cases we had convergence, because we had enough let's say, enough large gains on the joints that needed to have this strong proportional action. Another practical aspect is that we have assumed that we have reached at every time, at the end of each iteration, we have reached a steady state with zero velocity and with a constant position error. Now, if you look carefully in this, you may realize that those steady states are assumed asymptotically, so as time goes to infinity. So every single iteration should last an infinite amount of time. And since there are, in principle, an infinite number of iterations, each one contracting the error to zero, but not in a finite number of steps, we have a double infinite time to wait in order to converge. In practice, this is not true because we can set, as we did in this numerical simulation and also in the experiment that we conducted with this scheme, we set suitable threshold. And when we are getting close enough to the next steady state, which means that the joint velocities are close to zero, and the variation of the position is below, in a given interval of time, is below some small threshold. So we are practically stopping. So we can consider that as a practical steady state reached and update our feed-forward term in the iterative scheme. So this is really the difference between the theoretical results and its practical implementation. So we have done a number of experiments. This is quite an old piece of research conducted in our lab. And I would like to present you only one particular extension, dealing with a flexible robot that we have designed and built actually in our lab in the 90s. First of all, I would like to show you a couple of videos, very old-fashioned, I would say, concerning control problem for simple robots, a one-link robot and a two-link robot with flexible, distributed flexibility along the link. So on the left-hand side, you see a device which with a 70 centimeter long aluminum beam, which is very flexible in the plane of motion. So it can deform at the tip by an amount of, let's say, it's 70 centimeter long, about 15 centimeter, okay, from the rigid equivalent structure while moving. There's a heavy motor, a direct drive motor, so that you don't need to amplify torque because the structure is relatively lightweight, in fact less than 1 kilogram in total. And the task here was moving from rest to rest this flexible link without caring about intermediate deformation, so it's really a regulation task, but reaching the final new equilibrium with the undeformed link in a fixed amount of time, in this case 1 second. Okay? So you see that the evolution, okay, you see that you barely see vibration and oscillation, but during the motion, as you can see from the two snapshots taken from the video below, there is deformation. But indeed, at the final instant of time, deformation will be zero, motion will be zero, and we have reached the final equilibrium. So in this case, there was no gravity, and this result was obtained by applying PD plus a suitable feed-forward computed based on the model. The second short clip, I would say a few seconds, is the only trace that we have of the flex arm, which is the two-link experimental arm that we designed in our lab. The first link is short and rigid, the second link is flexible, again with sector that avoid torsion or bending under gravity. So the only deformation and vibration occurs in the plane of motion. And you can see here a special control law which allows the tracking of desired trajectory for the end effector of this flexible link, of this flexible arm, in planar motion. So the motion is 45 degrees for the first link and 45 degrees for the second link, and you see that we realize after some final transient the desired configuration. And we have made a number of other addressed and solved other control problem on this tractor, in particular on the second one, which has also a critical feature for those of you who are more interested in control. The end effector of this tractor has a non-minimum phase characteristic. So when we will talk about inversion control or feedback minimization control, this is not possible for such structure. So it's a quite challenging control task. But let's go back to our case. So the iterative learning control that I have presented for rigid robots, in fact, has been extended also to situations in which flexibility is present. And in fact, two types of flexibility. So rigid link, but concentrated elasticity at the joints because of the use of particular transmission elements like harmonic drives, or fully distributed along the links. Indeed, the problem is having gravity. So in order to test this on our two-link flex arm, it was called the DIS flex arm, this was the old name of our department, we have done a small trick. So we have moved the base, we have tilted the base from the horizontal by 6 degrees, so that the robot would fall, uncontrolled, would fall in the lowest configuration, straight downwards, let's say to the right in this picture. So we have included gravity in the picture. Iterative control can be used to regulate in those type of robots either the motor position, if you do if you have joint, flexible joint case, or the base of the flexible links. So it's like when you're having a long beam and you're controlling the base of the beam, not the tip. In fact, in robotics we are usually interested in the tip position of our structure, so at the Cartesian level. So I'm presenting here the version of this iterative learning control which achieve regulation at the Cartesian level. So while including all the flexibility. And for doing this, the iterative scheme has been slightly modified into a double iterative scheme. And we will see in the next slide how this was done. So first of all, the motion test, from which I'm presenting experimental results, is going from the straight downward configuration, so where the arm is straight. The first link, remember, is rigid. The second is the flexible one. But in this configuration, everything is in default. So we are pointing downward on the inclined plane of motion. And then the task was to move the first link to 90 degrees and having the tip angle at 0 degrees. So the flex arm would be deformed by the presence of gravity, but the tip would be at the same level of the prolongation of the first link, as if the robot had a second rigid link. Okay? So the double iterative scheme, which is taken from this old paper by myself and a former PhD student who is now a professor at Roma 3, Stefano Pansieri, includes the memory part, so the update from UI -1 to UI with the law that we have seen, the PD control, and everything is closed with reference to a desired position at the base of the robot. So this would be a single iterative scheme, which guarantees that we bring the base of the flexible link and also the base of the rigid link, the first rigid link, which is exactly equal to the tip of its of this segment, to a desired value. Indeed, this desired value should be corrected itself. We should have an external memory effect, so to correct the reference in such a way that the tip, the actual output of the system, the tip angle, is aligned with the first link, like in the picture on top left of this slide. So this is the double memory scheme, the double iterative scheme that is made recursively. And you can see that in the plots that in just 3 iterations we are able to bring the system in the desired configuration. Again, the first link position has some transient. You start with a pure PD control, and then you update the feed-forward term, and then you update also the reference position for the outer loop, and you see that the tip angle also converges to its desired value. So the first link goes to 90 degrees, the tip angle is 0 with respect to the 90 degrees of the first rigid link. Now, indeed, we had some sensor measuring the deformation. We didn't use at all this for feedback control, but we used for testing what was going on the flexible link. And you can see in the last plots that in fact there is a final deflection due to the presence of gravity. So despite of this, the tip of the second link is where it should be. And this concludes this lecture. Thank you for listening.